Yeah, so hi guys. I've been running this series on my channel for a while now, where I've been covering or sort of studying and learning Triton myself. All the videos so far did not have any audio cast. I thought about not having one for this as well, but I just thought maybe having one and seeing how it goes would be a fun thing. So this is again not meant to be a tutorial, and I am still a very much a beginner at Triton. So yeah, there's your disclaimer. I probably won't be speaking for a lot of the portions while I'm studying it, or maybe just reading out the text out loud. So yeah, here I go. Introducing Triton, open source GPU programming for neural networks. Right. We're, we're releasing Triton 1.0. I guess 2.0 is out now, an open source Python-like programming language which enables researchers with no code experience to write highly efficient GPU code most of the time on par with what an expert would be able to produce, right? So is the code the repo? Yeah, it's the repo. Hmm. All right. Okay. This is a documentation. So Triton makes it possible to reach peak hardware performance with relatively little effort. So if you want to write a floating point 16 meters multiplication kernel that matches the performance of QBLAS in under 25 lines of code. What exactly is QBLAS? GPU accelerator library for writing AI and HPC applications. Okay, and I've also heard this for Cutlass thing. So Cutlass is a collection of C++ template abstractions. Okay. Hmm. Okay, yeah, not moving away. Right. Yeah, I guess this is true. Under 25 lines of code. Our researchers have already used it to produce phones that are up to 2x more efficient. We're excited to work. Okay, so you use frameworks. While convenient, this approach requires the creation of template tensors, which can hurt the performance at scale, right? The issues can be mitigated by writing specialized kernels, and this is difficult. Alright, I can understand this. I had some operating system courses and they were a pain. I would assume GP programming is similar. And although a variety of systems have recently merged to make this process easier, we have found them to be iterative verbose, lack flexibility, or generate code noticeably slower than their handwritten baselines. This is why they created Triton. Alright. So challenges. The architecture of modern GPUs can be roughly divided into three components: DRAM, SRAM, and ALU, each of which must be considered when optimizing CUDA code. Okay. So memory transfers from DRAM must be coalesced into large transactions to leverage the large bus width of modern memory interfaces. Okay, that sounds reasonable. Data must be manually stashed to SRAM prior to being reused and managed so as to minimize shared memory bank conflicts upon retrieval. Okay, computations must be partitioned and scheduled carefully both across and within streaming microprocessors so as to promote instruction or thread level parallelism and leverage special purpose ALUs. Okay, so you have your DRAM or your high bandwidth memory of the chip. It goes to a memory controller. Then you have your SRAMs. Okay, reasoning about all these factors can be challenging even for seasoned CUDA programmers. The focus of Triton is to fully automate these so that developers can focus on the high level logic. Okay, This Triton aims to be broadly applicable and therefore does not automatically schedule work across SMs, leaving some important algorithmic consideration, like tiling inter-SM synchronization to the discretion of the developers. Okay, so Triton does memory coalescing on its own, it does shared memory management on its own. Scheduling across SMs is something which is needed to be done manually. Okay, what is an SM? Hmm. Streaming microprocessors. Hmm. SMs are streaming is a fundamental unit of computation. Okay, modern reviews comprise of multiple SMs. Hmm. So they are parallel processing unit. SMs are designed to execute parallel workloads and they contain CUDA cores. Each SM can concurrently execute multiple threads. These threads are organized into groups called WOPs. A WOP typically consists of 32 threads. Okay, and the SM processes these threads in a SIMD, single instruction multiple data fashion, where the same instructions, okay, memory and cache themselves their own memory resources, share a large pool of memory. Okay, specialized units SM may include specialized units such as tensor cores and NVIDIA's Volt and Turing. Tensor cores are specifically designed for accelerated matrix multiplication operations. Okay, task scheduling, and resource management. All right, now I have some idea about what's going on. All right, so the programming model. Out of all the domain-specific languages and JIT compilers available, Triton is perhaps most similar to Number. Okay, Number is another Python library. Kernels are defined as decorated Python functions and launched concurrently with different program IDs on a grid of so-called instances. However, as shown in the code snippet below, the resemblance stops there. Okay, I'll check it. Okay. Triton exposes intra-instance parallelism via operations on blocks, small arrays whose dimensions are powers of 2 rather than single instruction multiple thread execution model. In doing so, Triton effectively abstracts away all the issues related to concurrency within CUDA thread blocks. So all of these things. Let's see. So this is a GPU kernel in Number. Different instances of this may run in parallel. Okay, so you have add X, Y, Z, and N. Each kernel instance itself uses an single instruction multiple thread execution model where instructions are executed in parallel for different values of thread index, right? So you have thread ID, you have block ID, you figure out the index using by calculating like the shift. So block ID times the block size plus the thread ID, and then you do this addition if you're not out of bounds. Okay, now this is in Triton. Again, different instances may run in parallel. So up until this point, I guess everything is the same. Then there's just this comment. So in Triton, each kernel instance executes block operations on a single thread. There is no construct analogous to thread index. Okay, so you are working on only one thread instead of multiple threads, so you do not have this thread indexing. Okay, you get your program ID. Your block ID is now basically a program ID, and then you set up these offsets. So then you load up these. Basically, you have the starting pointer of X. You add these offsets, and you can load them up into memory, and then you can write it down into memory. So while this may not be particularly helpful for embarrassingly parallel computations, it can greatly simplify the development of more complex GPU programs. Okay, so consider, for example, the case of fused softmax kernel, in which each instance normalizes a different row of the given input. So standard code implementation of this parallelization strategy can be challenging to write, requiring explicit synchronization between threads as they concurrently reduce the same row of X. Most of this complexity goes away with Triton, where each kernel instance loads the row of interest and normalizes it sequentially using NumPy-like primitives. All right. So, see, I don't have much understanding of how CUDA works. So, these comparisons do not stand out to me, or I can't really appreciate how better this is. But I still get vague hints of what they're trying to get at. Okay, so I guess we've seen something like this already in weird uh, the tutorial page. But yeah, so you have all of these strides and stuff. Okay, you take the row index, column indices. This specific kernel only works for matrices that have less than block size columns. All right, yeah. Then you arrange this. You can compute the shifted x. So you take x, m times the stride of m, and n times the stride of n. This basically moves you along the rows, and this moves you along so column. Then you load it into memory, and then rest is negative float infinity so that your softmax works well. For numerical stability, you subtract the max value because this is a property of softmax. If you subtract the same value for every element, the softmax retains the same, and you write it down into memory. So this is how it works. Note that Triton treats x and y as pointers rather than tensors. It felt like retaining low-level control of memory access was important to address more complex data structures like block sparse tensors. Yeah, I guess, of course, they did it for a reason, and I think that makes sense because when you're doing GPU programming, if you do not have that low-level access, how much flexibility would you have it actually being comparable to lower level setups like writing pure CUDA? Importantly, this particular implementation of softmax keeps the rows of X in SRAM throughout the entire normalization process, which maximizes data reuse. This differs from PyTorch's internal CUDA code, whose use of temporary memory makes it more general but significantly slower. The bottom line is here that Triton is not that Triton is inherently better, but that it simplifies the development of specialized kernels. Right. So yeah, Triton seems to be a pretty much beating it everywhere. The lowest performance of the Torch version 1.9 jet highlights the difficulty of automatic CUDA code generation from sequences of high-level tensor operations. So what this is referring to the best of my knowledge, is basically you write a function and then you do add a flag decorator to do JIT compiling, which creates a graph, basically stuff which used to happen in TensorFlow. Uh, one TensorFlow one was always built this computation graph, which PyTorch later added, and then TensorFlow copied over the eager stuff in TensorFlow 2 and all that stuff. But yeah, so this is something which they the compiler sort of figures out how to write the CUDA code, but you can see that just from going from high level PyTorch code to CUDA code is not easy. Easy in the sense it's not easy to get an efficient implementation. Yeah, so this is that fused version. We just add this decorator. Matrix multiplication. Being able to write fused kernels for element-wise operations and reductions is important, but not sufficient given the prominence of matrix multiplication. As it turns out, Triton also works very well for those achieving peak performance with just 24 lines of code. Okay, CUDA would take a lot of effort and would even be likely to achieve lower performance. Okay, hmm. I can see a lot of effort here, of course. Writing, assembly, writing. This that was assembly, right? If I'm not wrong. Yeah, this is assembly code. ASM. Yeah, this is moving around registers, but I won't like commit to anything. It might just be something. else, which I'm not fully appreciating right now. But Hertz block sparse, efficient GPU kernels for block sparse matrix multiplications. Hmm, I've never heard of this library. Okay, 4 years old. Mhm. Still, I'll just leave a star. Maybe in the future it comes back. So this is the matrix multiplication. You get the block and group. You get the intermediate ones from for block and block K. Then you get the offset. Basically, you get PIDM is okay. So you divide it by group M, and then for the other one, then you calculate PIDN. So programs are grouped together to improve L2 hit rate. RM indices. Maybe ChatGPT can help me a bit here. Okay, A and B multiplies them and stores the result in C. M, N, and K are dimensions and strides, and then meta seems to be additional meta parameters. All right. These give you the block size for the matrix multiplication. Makes sense. So calculating a program ID for grouping programs to improve L2. This seems to be related to optimizing memory access patterns. Okay, the comment made me realize as much. So RM respective row number denotes a range of indices, and then for rows respective column. Okay, then you calculate a mhm. This is basically you take the pointer of A, and then this is getting update memory address of elements, okay, in the first block, and then you have this accumulator, and then you put that those accumulated values into C. So you accumulate a block of values and store them into C. Right. Yeah, makes sense now. One important advantage of handwritten matrix multiplication is that they can be customized as desired. So you can accommodate fuse transformations and outputs like having that leaky early there. Uh, yeah, so far so good. Triton with Rikireli also does pretty good. And this is better than Kublas plus George and Rikireli. So a high level architecture. The good performance of Triton comes from a modular system architectures around Triton IR and LLVM based intermediate representation in which multi-dimensional blocks of values are first-class citizens. So you have Python, then you get your Triton IR intermediate representation. Okay, then this gets compiled to LLVM. Okay, and then PTX. Okay, So this box the abstract syntax tree of the provided Python function to generate Triton IR using common SSA construction algorithm. I have no idea what that means, but that is a thing apparently. Then this code is simplified and automatically parallelized by a compiler backend before being converted into a high-quality LLVM IR, and eventually PTX for execution on recent NVIDIA GPUs, CPUs, and AMD GPUs are not supported. And okay, yeah, we have found that the use of blocked program representation via Triton IR allows the compiler to automatically perform a wide variety of important optimizations. So data can be automatically stashed to shared memory by looking at the operands of computationally intensive block level operations and allocating synchronized using standard liveness analysis techniques. Uh, I didn't really understand this part. Let me reread this. We have found that the use of blocked program representations via Triton IR allows a compiler to automatically perform a wide variety of important program optimizations. Okay, so for example, data can be automatically stashed to shared memory by looking at the operands of computationally intensive block level operations and allocated synchronized using standard liveness analysis techniques. Okay, so I guess it's something about reusing memory, but I'm not really sure. Live range. Okay, I guess it's something around that. Still, let me just check. So you can store that to shared memory so that other processes can also access it, I guess. Okay, so if a variable would be in use later, it gets stored, I guess. Yeah. And important, on the other hand, Triton programs can efficiently and automatically parallelize both across SMs by executing different kernels concurrently and within SMs by analyzing the iteration space of the block level operation and partitioning it adequately across SIMD units as shown below. You have this, okay, you vectorize it, then you have vector SIMD operations and then running it. Define a Triton program, then you have the iteration space, matrix multiplication is tensorized, then you map it onto your multiprocessors, then map it onto GPUs. Automatic each block level operation defines a block iteration space that is automatically parallelized. Okay. Right. Yeah, this is pretty cool. I think there's something else I wanted to cover as well. Probably not this because this is a large paper, but I think I had something else as well. Yeah, this. I'll drop both of these in the description if anyone's interested. With the success of deep learning and exploration of research papers, yeah, I guess I know this. PyTorch is one option, but it is a high-level compiler that can only optimize part of code that cannot be used to write custom CUDA kernels. But cannot be used to write custom. Okay, there's another problem with writing CUDA kernels. It is incredibly hard to do. I agree. Optimizing the computation for locality and parallelism is time-consuming and requirements often requires experts. Also, GPU architecture rapidly evolving. Got it. So this is where Triton comes into the picture. Triton has three main components: Triton C, Triton IR, Triton Chit. Okay. Interface to existing DSLs not addressed in this paper. Okay, this is a figure from the paper. So Triton C is a C-like language mainly intended for programmers already familiar with CUDA. Okay. Triton IR and LLVM based intermediate representation. So Triton IR programs are directly constructed from Triton C. In short, LLVM provides a lot of hardware-specific optimizations, which means we can directly use CUDA's compiler to optimize the code specific to the particular hardware. Triton JIT is a just-in-time compiler and code generation backend for compiling Triton IR programs into efficient LLVM bitcode. This also includes very machine independent optimizations, which means less work for us. Got it. The Triton JIT is the most exciting part of the Triton project for me. It allows programmers no experience to write kernels. Okay, so basis of GPU programming. So starting with CPU host, CPU has access to RAM, storage disk, and all peripherals. GPU on the other hand has no access to RAM or anything. Okay, GPU has its own memory, which is called VRAM. I guess it's video RAM, and data must be copied from CPU to GPU. And data must be copied back from the GPU to CPU for CPU to store it to the storage devices. This is the reason you should minimize data movement, because that is, I guess, the bottleneck. To do this, you have to brainstorm how you can load the same data and process it in parallel, import the data in a way that it can be reused multiple times before importing next data. Cool. So in CUDA, we launch many threads in groups of threads, which are blocks that form a grid. Okay, so you have a grid and you have blocks, and each block has multiple threads. So all thread in a thread block can communicate with each other. You can launch 1024 threads per block. Okay. The idea behind using blocks is that you do not need to change your code if you get a new GPU in the future. So the new GPU can simply execute more blocks concurrently without change of any code. Okay. So a CPU program versus a CUDA program. Let's say you have to add these two arrays in C++. If we want to add these, you can do this via for loop. But in CUDA, you launch three threads. Each of will do addition at one index. So the entire for loop happens in one place, in one step. So first array 1, array 2 will go to GPU. You'll create a new array. You'll launch three threads and then do this. Since GPU have thousands of cores, doing simple operations is uh, much faster there, and it justifies the loss in uh, the losses caused by data transfer. We saw code execution model above. Now let's see how Triton differs. In CUDA, each kernel is associated with a thread block. In Triton, each kernel is associated with a single thread. Okay, this is what we saw in the blog. This execution paradigm solves the problem of memory synchronization between threads, inter-thread communication, while allowing automatic parallelization. Okay, the problem of memory sync. I guess so. Yeah, since you have one thread, why would you need synchronization between threads? Now, instead of storing threads inside a thread block, a block consists of a range, tiles of pointers to threads. The interesting thing about this is you can have as many ranges as you want. So if your input is 2D, you can specify range 10 for the x-axis, range 5 on the y-axis for 50 threads. Okay, so if you have a block, you can create in CUDA you would have all of these, but in Triton you have only one. Each kernel is associated with a single thread. Let me just make sure I get this right. Each kernel associated with a single thread. Okay, so this is your grid, and the kernel is associated here with all of these threads, but here we have range 0 here and range 1 here, so only one. This is a figure from the paper. I would guess this is Do they have like a better hmm, uh, explanation? Just the Triton is similar, but each kernel single thread are automatically parallelized and associated with a set of global ranges that vary from instance to instance. If you guys think, okay, yeah, I guess my understanding is correct here. So, how does adding to arrays work in Triton? You first define a block. We know blocks are defined by specifying a range. So, in addition, we only need to define range along one dimension. So, let it be 512. So, a range of 512 means you will be launching 512 threads in parallel. Now you index, we get the index of the input data. Suppose the array is of size 1000. Because we define a block size 512, we will process the input array in chunks of size 512. So the first would be this and this. Okay, this is done using the code below. So you get this process ID offset, and then you get these offsets. Masking to guard memory operations. So in the example, since array size 1000, you want to mask off stuff, and you can add this mask parameter. Then you can just do the arithmetic and store it, and this is your entire kernel. To use the kernel, you need a helper function. So grid is basically specifying the space over which you will work. In our case, the grid is 1D, and this is why how the data is split along the grid. So if the input arrays are of size, then we want to have the grid as this. So in this step, we are basically specifying how. Okay. By default, grid takes one version argument which is called meta. Meta. The purpose of meta is to provide information like block size, but we use a global variable to define that. Okay. Now we want to call the add function as a normal Python function and make sure inputs to a function are already on the GPU. Mhm. And you get this output. Uh, did you get? Hmm. Okay, you're comparing the output difference. How do you work with higher dimension tensors? You can reuse the same kernel for n-dimensional tensors. This gives us the flexibility to avoid writing multiple kernels for different input dimensions. The idea is simple. We reshape the tensor to a 1D tensor in the helper function and reshape the output tensor. The reshaping operation is not a time-consuming operation as we are just modifying the stride values in a tensor class. Let us see. So if you had this, you got the shape. This reshapes it to a 1D tensor, and then you create output of the same size and get stuff back, and then you reshape it again. Yeah, I think this was a good add-on for my understanding. I'll probably go over the Triton paper next, try to understand stuff there. I probably won't understand a lot of it because I do not have a background in compilers and stuff. But yeah, so far so good. Let me just add this into my notes as well. Thank you.